Hello everybody, welcome to this video giving a brief introduction to parametric curves. So now we're going to change topic, stop looking at Taylor series and instead focus on doing calculus with parametric curves. But first in this section, we just want to get an idea of what a parametric curve is and how we can sketch parametric curves. So let's get started. And what is the motivation? So the motivation is look at a curve like this, as is pictured. Then the problem is we can't write it as y in terms of x, nor can we write it as x in terms of y. So this was the way we represented curves before, right? We either had y in terms of x or x in terms of y. So why can't we do that here? For instance, if we pick an x, a point x on the x-axis, then there is more than one y. For instance, if x is over here where the cursor is, then there are going to be three different y values. So that means we cannot write it as y equals f of x, because if we write it as y equals f of x, we plug one x in, we get one y out. Whereas here we plug one x in, there are supposed to be three y's. So we can't write it in that way. And similarly with x equals g of y. So there are some y's where there are more than one possible x value that lies on the curve. Whereas if we go to write it as x equals g of y, we plug in one y value, we get one x value, which is not the case here. So this curve, for each x, there's multiple y, and for each y, there's multiple x. We can't write y in terms of x, nor can we write x in terms of y. So we need some other way to write the curve. And one way to write the curve is as a parametric curve. We instead of writing x in terms of y or y in terms of x, we can write x and y in terms of something else, which is typically called a parameter. So we can write x as a function of t and y as a function of t. And the parameter t varies. And as we plug in different t's, we get different points on the curve. And if we put them all together, we get the curve itself. So sometimes we'll have restrictions on what t we can plug in, and sometimes we'll just be able to plug in any real number t. It just depends on the curve. But this is the key point. With parametric curves, x and y depend on something else, which is called a parameter. Often we call it t, but it could be anything. It could be theta. It just depends on the context. So let's see some examples. Let's try to sketch and identify the curve defined by, let's say, x equals t squared minus 2t, y equals t plus 1. And we get different points on the curve by plugging in different values of t. So let's plug in some values of t and see what points on the curve we get. So if we plug in t equals -2, then x becomes -2 squared is 4 minus 2 times -2, so that's plus 4. So we have 4 plus 4, x equals 8. And then y is t plus 1, which will be -1. So plugging in t equals -2 gives x equals 8, y equals -1. So the point 8, -1 is on the curve. Similarly, with t equals -1, it gives us 1 plus 2, which so x equals 3, and then y equals -1 plus 1, y equals 0. So the point 3, 0 is on the curve. And then so on and so on for different values of t. We just pick some t's that we want to substitute where we can easily compute the point. So t equals 0 gives x equals 0, y equals 1. Okay, and then we get -1, 2, 0, 3, 3, 4, 8, 5, and so on, just by plugging in different t's and calculating x and y. So now we have a whole bunch of points and we know that they are on the curve. So we can just plot those points. So here I plotted those points and we know the curve joins them. So we just kind of make a rough sketch by joining the points with a curve. So here are the points we calculated on the last page. It was something we did concretely, right? We can just calculate them, we just plug them in, and then we just join them with a curve. So the curve looks something like this. So it looks a little bit like a parabola. So this was one way of sketching parametric curves. We plug in the parameters, we plot the points, we sketch them by a curve. Here is a rough sketch of the curve. Another way we can sketch the curves, or maybe a way we can confirm what it looks like, is by eliminating the parameter t and writing y in terms of x or x in terms of y. But as we just said, that does not work for every curve. Like a lot of parametric curves, you cannot write as y in terms of x or x in terms of y, or maybe you need multiple equations to do that. But this curve, it was a pretty simple equation, so we can write it actually x in terms of y or y in terms of x. So let's just rearrange to get rid of our parameter. So we are trying to get rid of t here. So y equals t plus 1, that's the simpler equation. The other one will be kind of hard to solve for t. But the easier one to solve for t is y equals t plus 1. We get t is equal to y minus 1. And then we plug that into our equation for x to get rid of the t in that equation. We get x equals t squared minus 2t, replacing t by y minus 1. We get y minus 1 squared minus 2 times y minus 1. If we expand all that carefully, we get y squared minus 4y plus 3. And if you were to complete the square on this, you would see that this is actually the equation of a parameter, of a parabola. So just once more, I want to mention that here we did manage to write our parametric curve x in terms of y. So it would have been harder to write it as y in terms of x, but at least we wrote it as x in terms of y. But that's because we were kind of fortunate and it was quite a simple curve. So if we start with the general parametric curve, sometimes you can write it with an equation with x in terms of y or y in terms of x, or maybe an implicit equation, but not always. It just depends on the example. Anyway, we have two methods of sketching. One is plot the points and put things together, and the other is to try to eliminate and find an equation in terms of x and y. Okay, let's see maybe a couple of other curves, and then we'll do some more complicated ones in class, so I don't have to draw things too much here. So the one thing we can do is also give our curve start and endpoints, maybe by restricting the values of the parameter. So in the previous example, t could just take any value, whereas now we can, if we want, we can restrict t to lie in some range. So if we have a parametric curve y equals f of t, sorry, here should be x equals g of t, then we can say that t lies between a and b. Then the start point will be what we get when we plug in a. So we'll have f of a, g of a. And the endpoint will be what we get when we plug in b. So it will be f of b, g of b. So let's see an example of a curve like this. So for instance, what curve is represented by the equation x equals cosine t, y equals sine t for t between 0 and 2 pi? If we were to plug in some points, so for instance, you could plug in t equals 0, you get 1, 0. T equals pi over 6, you get root 3 over 2, a half. T equals pi over 4, you get root 2 over 2, root 2 over 2. T equals pi over 3, and then t equals pi over 2, and so on, and you could go around the unit circle. If you plug in some points, then you get suspiciously something that looks like the unit circle, and it actually is the unit circle with center the origin. So that's what we see, or that's what we guess from plugging in points. One thing we could do is to try to get an equation involving x and y. So here it's quite hard to get x in terms of y or y in terms of x, but it's very easy to get an implicit equation. For instance, we know that sine squared plus cosine squared equals 1. So if we do x squared plus y squared, then x is going to be, then we're going to have cosine squared t plus sine squared t, which is going to become 1. So it turns out this is a circle, center the origin, and radius 1. And if we want to think which way around we go, so parametric curves, as t varies, that means that the point along the curve moves. So if t starts at 0, we start at 1, 0. And as t increases, we move towards the point 0, 1 when t equals pi over 2. So here we're going around in the counterclockwise direction. So parametric curves also tell us more information. They tell us where we start and where we end if we have start and end points. And it tells us what direction we move around the curve. Okay, let's see a very similar example, x equals sine 2t, y equals cosine 2t. So rather than starting with cosine t sine t, we have sine 2t cosine 2t. So what is going on here? Again, we can do the same thing because we know that sine squared plus cosine squared equals 1. So if we do x squared plus y squared, here we should get sine squared 2t plus cosine squared 2t, which is going to be equal to 1. Okay, here is a 2t, but it doesn't make a difference. So again, we're moving around the circle with center the origin and radius 1. Okay, but what is the difference? Well, the difference is that here, if we think about what points we get as t increases, if we get to t equals pi, then we get to sine of 2 pi cosine of 2 pi. That's the same as where we start because sine and cosine are 2 pi periodic. And then we do the same thing again when we get to t equals 2 pi, we get sine of 4 pi cosine of 4 pi, which is the same. So we go through the start and end point at the beginning and in the middle and at the end. So here we actually move around the circle twice. And when t equals 0, we start at x equals 0, y equals 1, because sine and cosine have switched around. So here is what it looks like. We start at 0, 1. Rather than moving in the counterclockwise direction, we move in the clockwise direction because the sine and cosine are switched. And because the angle is 2t, we go at twice the rate, or twice the speed. So we go around the circle not once, but twice. Okay, more generally, so we saw quite a bit the circle, center the origin, and radius 1. We could make some simple tweaks to get the circle with a center AB and radius r. So if we multiply cosine t and sine t by r, then that expands the radius by r. So r cosine t, r sine t, just by itself, would give a circle of radius r. And then if we want to move the center from 0, 0, we should add a to x and b to y. That will give us a circle with center a, b. So in general, the curve x equals a plus r cosine t, y equals b plus r sine t represents a circle with center a, b, and radius r. For instance, if you wanted to confirm this, then you could solve for cosine t and sine t. You would get cosine t as x minus a divided by r, sine t as y minus b divided by r. And then we do cosine squared t plus sine squared t equals 1, because sine squared plus cosine squared is always equal to 1. We get an equation involving just x and y. It will be x minus a squared over r squared plus y minus b squared over r squared equals 1. You rearrange, you would get x minus a squared plus y minus b squared equals r squared. So you would have the equation of the circle in the usual x and y coordinates. Okay, and this curve also goes around the circle once because we just have cosine t and sine t between 0 and 2 pi. So we don't go around more than once. And it's in the counterclockwise direction because the cosine is on the x coordinate. Okay, so as we've seen, parametric curves, the kind of most examples we saw are simple, but as we saw right back at the start, the advantage of parametric curves is that they can represent curves that are more general than just y in terms of x or x in terms of y, and they capture how we move around the curve, which is not something that we normally see when x is in terms of y or y in terms of x. And we saw two ways to plot the curves. We can either, as we saw at the beginning, we can plot the points and just join them together to get an idea of what the curve looks like. Or we could eliminate the parameter maybe by solving for the parameter and subbing into the other equation. So we could get y in terms of x or x in terms of y. Or we could use some kind of identity we know. Maybe here we use sine squared plus cosine squared equals 1, but there are other trig identities and other things like that too, to get an equation involving x and y. And then it would typically be an implicit equation. So that's a curve where x and y are related by some equation. So that is something we'll see. And in class, we'll see some more examples of parametric curves. They're all going to be kind of similar, just a similar idea of trying to sketch them. One kind of more complicated example maybe we'll touch on is going to be the cycloid. Okay, thanks everyone. See you next time.